So we see that if they successfully complete, the grow algorithm and the shrink algorithm will produce linearly independent sets of vectors. Let big V be a vector space. A basis for V is a linearly independent set of generators. So a basis for big V is a set of generators with two properties. The vectors span big V, and the set of vectors is linearly independent. So this is the most important definition in all of linear algebra. Here are some examples. We know that the basis must satisfy these two properties, spanning property and the independence property. Let big V be the span of these three vectors. Is this a basis for big V? Well, no. We've seen that though this set is spanning, it's not linearly independent. In fact, here's a linear combination, a non-trivial linear combination that equals the zero vector. So it's not a basis. On the other hand, if we take one of these vectors out, it is a basis. It's obvious that these vectors are linearly independent because this one has a non-zero entry in a non-zero first entry, and this one has a zero first entry, whereas this one has a non-zero second entry, and this has a zero second entry. So using an argument described earlier, we can show that any linear combination that equals the zero vector must be trivial. How do we show, though, that these two vectors are spanning? Well, we can write the third vector, the missing vector, as a linear combination of these two vectors. Therefore, by the superfluous vector lemma, the set spanned by the three vectors equals the set spanned by the three vectors minus the third vector. Here's a very simple example of a basis for R3. These are the standard generators. It's easy to see that this set of vectors spans R3 because for any vector in R3, we can easily write it as a linear combination of those three vectors. We can argue as before that these vectors are linearly independent. Suppose you could write 0 as a linear combination of these vectors. Let's add up the linear combination. We get alpha 1, alpha 2, alpha 3. Well, if that's equal to the 0 vector, it must be that alpha 1, alpha 2, and alpha 3 are all 0. That is, that the linear combination is trivial. So that shows those vectors are linearly independent. Now, instead of standard generators, we'll call them standard basis vectors. We refer to the set of these vectors as the standard basis for R3. And in general, the standard generators are really called standard basis vectors. Here's another example of a basis. These vectors form a basis. To see that, we have to show that they're spanning and that they're linearly independent. First, to see that they're spanning, we can write the standard generators as linear combinations of these new vectors. Since the standard generators can be written in terms of the new vectors, it follows that every vector in the span of these standard generators is in the span of the new vectors as well. Since the span of the standard generators is R3, that shows that R3 equals the span of the new vectors. Now we see that the vectors are linearly independent. Suppose we write the 0 vector as a linear combination of these vectors. Summing it up, we get this, and equating corresponding entries, we see that x plus y equals 0, x plus y plus z equals 0, and x plus z equals 0. Now, if we plug x plus y equals 0 into the second equation, we see that z equals 0. We plug z equals 0 into this third equation, we get x equals 0. And we plug x equals 0 into the first equation, we get y equals 0. So that shows that the linear combination is trivial. And therefore, these vectors are linearly independent. Now, in graphs, one kind of basis is a set of edges forming a spanning forest. The fact that it's spanning follows from the fact that for every edge x, y in G, there's an x to y path consisting of edges in the set. The fact that it's linearly independent corresponds to the fact that these edges form no cycle. So here's an example of a spanning forest in the graph. There are no cycles, and every edge in the original graph has its endpoints connected using edges in the set of dark edges. Here's another example of a spanning forest for the same graph. Now, we'd like to say that every vector space has a basis. We have a good approach to doing that. The grow algorithm and the shrink algorithm provide linearly independent sets that span a given vector space. So we'd like to say that those algorithms prove that every vector space has a basis. But we're not quite there yet. The grow algorithm corollary states that if the grow algorithm terminates, it terminates with a linearly independent and spanning set of vectors. But we don't know whether the grow algorithm always stops, whether it successfully completes. Now, the shrink algorithm corollary states that if we can run the algorithm, at the end, it'll give us a linearly independent and spanning set of vectors. But in order to run it, we have to initialize the set S with a finite set of vectors that spans the vector space. So we haven't shown yet that there is even a finite set of vectors that spans every vector space. Now, this is not a merely technical matter. In the wider world of mathematics, one has to deal with vector spaces for which there's no finite set of vectors that span it. In this course, however, we're going to keep things simple, and it'll turn out that every vector space does have a finite set of generators, and that every vector space has a basis. There are two natural ways to specify a vector space. One is by specifying generators for that vector space, and the other is specifying a homogeneous linear system whose solution set is the vector space. So this raises two fundamental computational problems. Finding a basis of the vector space given by generators, that is, given a list of vectors, find a basis for the space spanned by those vectors, and finding a basis for the solution set of a homogeneous linear system. That is, given a list of vectors, say A1 through AN, find a list of vectors that form a basis for the set of solutions to the homogeneous linear system A1 dot x equals 0, and so on.